You know it's extra snap.
Yeah, linear land, and today,
Is there another one?
yeah, we're gonna do a cross-cultural exchange today.
Uh-oh.
Between linear land and angle
exchange
base.
student? That's never good.
Let's just look at it at least.
Okay, so cross-cultural exchange. We looked at, the other day, I'm not even gonna write them down. We looked at a bunch of angular quantities that were the angular analogs of the linear quantities. So instead of displacement in linear land, what do we have in Anglevania? Angular displacement. Right here, I'll just write the variables down. So delta x becomes what in
Delta
Anglevania? Delta
Theta.
theta. Good. Oops. There we go. Velocity in linear land becomes what in Anglevania? Angular velocity. And what's the, it's not a W, remember what it is?
It's a W.
It's kind of a W. It's omega.
The W.
Omega. And we said that acceleration becomes what?
Alpha.
Alpha. Angular acceleration alpha. And all of the same stuff that worked, all the kinematic stuff that worked previously still works. That's the great thing, right? Everything we did in the past, all those relationships hold in Anglevania. So you get just doubled your knowledge of physics in the blink of an eye. Okay, but there is another issue we got to deal with that is a little bit different. It bridges the gap between the two. So if we were to take let's take two circles, two concentric circles. So there's one, and here's another. Okay, close enough. So they're both centered on this point right here. Okay, now if 2 points were two dots of paint on these hoops, let's put one of them there and one of them there. If we were to spin this around through one complete revolution, in Anglevania, have they traveled the same distance or different distances? Same distance. In linear land? Different, right? If we were, for example, let's say that these are the inside and the outside of a washer-shaped merry-go-round, right? And there's a person sitting on the inside with a can of spray paint that's going to paint a line all the way around. It's going to hang it on the ground as it rotates around. You're going to create a line, that circle. Person on the outside is going to create that circle. Okay. What's going to be the difference between the two? Which one's going to be darker? One on the inside. How come?
Less paint.
Because it's same amount of paint, a smaller circle, right? So there's a difference there. Okay. We could describe the linear. We call these the tangential quantities, by the way. As something rotates, the distance traveled, or the speed at which it's traveling, or even the acceleration that it's experiencing in linear land, we call those tangential quantities, right? Like if you were, this could just as easily be a car going around a corner. So here's the car seen from above, and this is the corner, right? The two cars traveling along these different corners, if they make one complete circuit in the same amount of time, in Anglevania, they've certainly traveled the same angular distance, right? Do the same angular displacement. But clearly, the speedometer out here is going to be a lot higher than it is in there, right? Okay. So what do you think the relationship's going to be? How are we going to calculate the linear speed, meaning the tangential speed? How fast is this car moving at any instant in time? If I were to draw the velocity vector, what would it look like if it's traveling along the blue track?
Tangent.
It's tangent, isn't it? Because the direction that it's pointing, the direction of the velocity at that instant is going to be like that, right? If you were to, if I'm swinging a rock around on a string and I clip the string, in which direction does the rock fly? So for example, if this is the string right here that's connecting that rock to the center, if I clip it right there, clip the string, in what direction does it fly? Straight up, not out at an angle, right? People oftentimes think that, but it doesn't. It's just going to fly straight up because that's the direction of its velocity when we clip the string, right? Okay. Okay, so we want to, first step is we want to see if we can come up with a way to predict what the tangential speed is. Okay, let's start off though with tangential displacement, right? So this goes back, so a bunch of you have already been in trig, right? So in trig, remind me, what's the relationship between arc length and angle for a circle? Right, so we'd say that if we've got some circle, there's my circle. And let's say we're going to go from there's the starting line. And we're going to rotate some object through an angle of pi fourths. So it's going to go through pi fourths radians, same as how many degrees? 45 degrees. And so this is angle theta, 45 degrees, which is the same as pi over 4 radians, right? How would we convert that again if we wanted to start with 45 degrees and we didn't remember or it wasn't a convenient place? How would we go through the conversion process of turning that degree angular measurement into radians?
Pi over 180.
Pi over, okay, pi over 180, good, we've multiplied. 45 degrees times, you gotta have degrees on the bottom and radians on the top, right? So 180 degrees is equivalent to pi radians. Or you could do 360 and 2 pi if you wanted. This is just a reduced fraction, right? And that's gonna give us pi over 4 if we do that, right? Okay, so if we go through an angle of pi fourths radians and the radius is r, how far has the ant traveled along the edge of the circle?
Isn't it r times the, how much radius it is?
It is. It's r theta, right? Has to be in radians though, right? And that makes sense, doesn't it? Degrees are arbitrary, so it would vary from, country to country depending if we all had different ways of subdividing circles. The degree part's pretty arbitrary, but the radians is not, right? So our formula is arc length equals r times theta, right? Where, I won't even put vectors on because the vectors are confusing. Radius times the angle gives us arc length, right? So that's useful if we wanted to know, for example, let's say if a person is riding around on a merry-go-round and the radius of the merry-go-round is r, right? And we know that they have twisted through, let's say, 1/2 of a revolution. Well, then we could easily find what their linear distance that they traveled was, right? Same thing as arc length. If they were painting a spray can on the ground as they went, how long would the arc have been, right? If you straightened it out. Okay, there's our relationship. Okay, so if that's the case, then what do you think? Let's make a prediction. What do you think that how is linear velocity going to be related, do you think, to angular velocity? If the radius is fixed, what do you think?
It's gonna be r theta per seconds.
Okay, yeah, we're moving in the right direction. Now, we could actually do a little calculus here. If you're not in calculus, don't worry, don't panic. It's not a big deal, but a lot of you are in calculus, so help us out, right? In this situation right here, is anything constant? R is constant, isn't it? Right? But theta is changing, and so is arc length is changing.
Find the derivatives, and then you get velocity.
Yeah, look what we could do. If we differentiate both of these with respect to t, what do we get? that one's gonna be S dot. Well, what is S dot?
Rate
Rate
of
of
change.
Well, okay, right, but S is a distance, right? So S dot in this case would be the same thing as V, wouldn't it? Right, everybody see that? R is a constant, so we leave that there. What's theta dot? That's just the d theta dt. Think what that is. What's theta dot?
Rate of change at the angle.
And what did we say that was?
The omega.
Omega. Yeah, that's angular velocity, isn't it? Think what angular velocity is, the rate of change of angle, right? So whether you did it via calculus or not, we end up with the same formula, right? Linear velocity equals radius times angular velocity, as long as we're moving in a circular path, okay? All right, last one. So what do you think then, just by going one step further with the calculus, what do you think the relationship is going to be between tangential, and we need that t there, tangential acceleration and radius? Yeah, I'm just going to differentiate again, aren't I? Right?
Rate
So the derivative of tangential speed, I'll put the t there, just remind us that it's tangential, is going to be, with respect to t, is v dot. Well, that's acceleration, right? And that's equal to my constant r times
alpha.
alpha. Yeah, what's the derivative of omega with respect to t? That's alpha, isn't it? Right? And from a calculus perspective, that makes sense, right? So look at those relationships that we get. Okay? So just try one of these here. Try one of these on your own. Just get a piece of scratch paper. Try that. So in this question, when they talk about, so in a bike shop, a bike wheel with a radius of 729, ooh, you know what, that's supposed to be diameter. Yeah, that's too big. I actually tried to base this on real. I gotta fix this. Hang on. No, it'd be a little different.
Oh.
Goes around about 1.5.
There you go. Okay, try that.
It's not totally fast.
Okay,
Like, I
so
can't
my
think of a reason
point
to
here I
break
wanted to
shop
make
like
was, when you read these things, you gotta
No, it's fast.
pay attention to the context. Because when it says something like, the bike with a diameter of 522 millimeters spins in place at a constant speed of 99.3 revolutions per minute. So it says speed, but what's implied about that speed? What kind of speed are we talking about? Constant. Okay, it's gonna be omega, isn't it, right? Because the units are units of angle over time, right?
Can you go back to that slide? You kind of everything written out like formulas instead of that?
Sure.
Alright, just for a second.
Yeah. Right there. So I'll add these to our growing list of physics equations and post them on Moodle. Okay, we good with that?
Yes.
Okay. So then a piece of gum is stuck on the bottom of one of the tires. How fast is it going to move tangentially? What's the tangential speed going to be? Well, what would we have to do here?
Find radius.
Find the radius, okay? So we need R.
What's the thing on acceleration?
Angular acceleration.
Yeah.
What random ones?
Okay, but if it's, now look, if it's if it's spinning in place at a constant angular speed, we're not gonna have any angular acceleration, right? But we do have, okay, we do have an R, don't we? What's that gonna be, what's half of 522?
261.
261, and those are millimeters. What units do we want that to be in? Meters. So what's our radius gonna be in meters?
0.261.
Okay, good. So we get R equals 0.261 meters. Okay. What's omega?
Do we wanna convert that?
We have to convert it, don't we? Yeah. So omega right now is expressed in terms of revolutions per minute, right? So 99.3 revolutions per minute. So let's get in the practice of multiplying by the changers all at once. So we want to end up with what units for omega? Radians per second. Okay, so we got to go from revolutions to radians. So what unit goes on the bottom? Good. On the top we get radians, and our good changer there would be 1 revolution is 2 pi radians. Good. Okay, make sense? Okay, and that's just because, remember, there's 2 pi radians in one circle. Okay. And then the other changer we would need, so that's going to get us from revolutions to radians. Okay, now we need to get rid of minutes on the bottom in favor of seconds. So what unit goes on the top? Minutes, good. And the reason, so we can cancel them, right? And then seconds on the bottom, and what's a convenient number?
1 minute per 60.
1 minute, 60 seconds, good. So we can just multiply straight across the whole thing. So 993 times 2 pi divided by 60 is what?
10.4.
About around 10.4-ish, okay? And that's a calculator number that we'll save, right? Radians per second. Okay, so now if we have a radius and we have an angular speed, now we know how do we calculate a tangential speed? What was that formula? If you don't remember, think in terms of units, right? Remember, radians don't really count, right? So right now, I've just got like per seconds, literally, is what we'd say. Radians are, they're a false unit, right? So I need meters on top. So if you're wondering which way it goes, it's pretty easy to think about, isn't it? V must equal omega times R. I usually write it the other way. R omega. Right? Because there's our meters and there's our per seconds. Now, I don't want you to get in the habit of just always, thinking in terms of just units. But in this case, it's a simple relationship between these 3 quantities, and that's the only way it could work, isn't it? Right? Okay? So what do we get then? If we, in the calculator, if we multiply 993, Lily, times your calculator number, 10.4, what do you get?
993 times 10.
Yeah.
How would you do it?
Whoops, did I mess something up there?
0.261.
That would be
10.
2.7.
No, but then you do point.
No,
No, the point, wouldn't we multiply by the radius,
By the,
not the,
yeah.
Oh, whoops, sorry, by the
Yeah.
radius, yeah, sorry. We're gonna multiply this by the radius, yeah. So 10.4-ish times 0.261 gives us what?
2.71.
2.71 to 3 places.
Yes.
So 2.71 units would be
meters per second?
meters per second. Okay, so let's try that. See if my programming is okay here. I don't know, we'll see.
It's just, everything's written out here. Meters per second.
Yeah, so then I want to go meters per second. Let's see how we're doing. Worked, how about that? Okay,
Yay!
good. All right. What if, okay, here's another one. I gotta to make the same change real quick. Give me just a second.
You have to change that one too.
Yeah, just take a second.
You go do it.
You're not.
Well, sometimes it's overkill.
I know.
Okay, I think it's fixed. Yeah. All right.
You guys work on skeleton.
Okay, try this guy. What you thinking on this one? What's that? Is the answer? Maybe.
That's what I'm thinking.
Oh, okay. How are we gonna approach this one? What are we looking for?
Looking for distance travel.
Okay, distance travel. All right.
So it's gonna be the same as the last one, except an extra step.
Okay, you could do it the same as the last one with an extra step, couldn't you? You have really a couple options here. You could, if you wanted to, you could calculate what the tangential speed is, and then once you know the tangential speed, isn't that really the speed at which the bike is traveling across the ground? Do you agree? Right? Because the wheels are spinning, but they're in contact with the ground, and so the ground is going by the bike as fast as the wheels are spinning, right? So then you could calculate that and then just multiply by 15.3. What's another approach you could take to this?
Find how many revolutions you go.
You could, right? You could also do most of this in Anglevania. You get the same answer, right? In Anglevania, we could say, okay, if this is my angular velocity and this is the time, in Anglevania, I could just use kinematics equation 1 to figure out what's the angle I traveled through, right? And then if I figure out what's the angle I traveled through, if I knew what the radius was, which I do, right there, that's down, but I can find the radius, then I could multiply the angular displacement by r to find the linear displacement. Either one will work, right? Okay, so I won't even go through it. You could do it. Okay, one more question for you, just to kind of set us up for tomorrow. Oops. So if we go back to our picture here, right here, we said that this was the velocity vector, right? That was the tangential velocity vector. What about acceleration? In what direction is this thing accelerating? Tangentially.
Positive.
Wouldn't it be in the same direction as the velocity? Right? Instantaneously? Right?
Positive.
Depends on your,
It could have to make
are you talking linearly and or angle weight?
I'm talking linear, right? I mean, think about what's going on. If this thing is being pushed so it's accelerating, well, the direction of the velocity must be the, right? Okay, but that's not what's happening. The thing continues to spin in a circle, right? Even as it picks up speed, right? In fact, even if we were spinning it at constant velocity, or if the car were driving around the circular track with the cruise control on, if I look a split second later, when the car's up here, in what direction is the velocity vector pointing now?
Negative, it's negative.
Well, it's pointing kind of in that direction, right? But it's changed, hasn't it? Right? So what's going on? I mean, it's accelerating even if it's traveling it with the cruise control on around that circular track.
Has a vertical component, that decrease.
Yeah, the vertical component has, the horizontal component has increased, right? But what's happening there? It's accelerating. It has to be, right? Because what is acceleration? Acceleration is the rate of change in velocity. Velocity is a vector quantity. So even though the length of the velocity vector has stayed the same, it's changed direction, and that constitutes acceleration. It's changed. Okay, so even if we ignore the fact that this thing, I mean, if we're speeding up the rate at which it's rotating, if there is some angular acceleration, then yeah, there is going to be some part of the acceleration that's going to be along the tangential direction. But there must also be some other kind of acceleration that's acting in a different direction here. Because even if there is no angular acceleration, it's still accelerating because it's changing direction. Okay. Does anybody want to hazard a guess in what direction the acceleration is acting, even if this car is traveling at constant speed?
Inward.
Inward. Yeah. Prove it. Prove it. It's hard to think of it with a car, but what if I have a rock on a string? And it's in, what were you saying, Richard?
There's tension.
Tension, yeah. So we could go into deep interstellar space where there's no gravity. And if I swing a rock around on a string, it's still going to go in a circle and there's still going to be tension. So the only force acting on the rock is tension. In what direction is the tension vector acting? Right there? It's towards the center, right? Has to be. Because it's a line, and lines are flexible. If the tension were acting in a different direction, the line would adjust itself and change, right? So tension always acts along the line. Yes, sir?
Can you calculate the average tension in a swing?
We can't, we'll be able to do that in a couple of days. We'll be able to do all that stuff easily. Yeah.
So, but if you did it in a whole circle, it'd be zero.
No, you can't, okay. You can't think of it that way because the tension's changing. It's changing direction. Now, what Nick's getting at is something, he's thinking along these lines. Correct me if I'm wrong. You're saying, okay, the total displacement from there to there is zero,
Yes.
right? Okay, what is total displacement? Total displacement is the change in position, right? Okay, but what's the change in tension? That's kind of a weird concept, right? We're getting prepared to talk about that in the near future, but just as we're leaving here, because it's a good question, what do you think happens if I apply a force to something over a distance? You know. I mean, if I apply a force to an object over a distance, it accelerates, right? Okay. So if tension is changing the direction of this thing, then perhaps there's some way of storing up that
Is it gonna be able to not?
No, it's not gonna be, not good enough. Anyway, we're, okay, we'll continue this discussion tomorrow. I'll put another problem set on for you, short one.